I'd like to introduce Dr. Kazunori Akiyama. He's a research scientist at MIT Haystack. He completed his PhD from the University of Tokyo in 2015 and has since been a fellow at the MIT Haystack Observatory, first as a JSPS postdoctoral fellow and then later on as a NRA Jansky fellow since 2017. He's been working as an MIT research scientist since 2020, and his primary research interests are extreme environments in the vicinity of black holes, and as explored by event horizon scale observations using VLBI with the Event Horizon Telescope. So this includes the development of new imaging algorithms and software packages for the Event Horizon Telescope, which we used to create the first ever black hole images. He joined the team of the Event Horizon Telescope in 2010 and has led the imaging working group of the Event Horizon Telescope collaboration since 2017. I'll leave it to Dr. Akiyama to take it away from now. Thank you.
First of all, it's a great honor to give an overview of radio astronomy imaging techniques on behalf of a radio astronomer. This is actually pretty classic techniques. The first imaging technique was actually proposed in the 1970s, so it's now like 50 years old. And it's just a great honor. There are many smart radio astronomers actually produce a lot of smart algorithms, but I have a chance to give an overview on behalf of them. So my scope of this talk is actually, I just want to give an overview of techniques, particularly, what is the concept of the image reconstruction techniques in the radio astronomy side from the traditional and the new or forward modeling techniques. So I don't want to go details about, mathematics and, details about techniques so that you can grab, the underlying idea and what actually drives the development of imaging techniques, even actually 50 years old of the radio interferometric imaging. So when I talk about the imaging techniques, I usually show, how imaging is important. I started to develop imaging techniques for the Event Horizon Telescope around 2015, and one of the striking imaging at that moment was this image. So this image is actually, it's not a radio interferometric image, but just this is a photo taken by NASA's New Horizon of Pluto. And then just image is spectacular. What I learned in a textbook when I was a high school or mid-high school student was this one. It's just circular, but I really can't guess, what is these blobby things, but now we have a spectacular images. And of course, this image provided, pretty much rich information, which we didn't have, prior to the New Horizon. And this is also happening in the radio astronomy with a new instrument. One of the striking images is the protoplanetary disk images taken by ALMA. And previously we only have a just point-like emission, and we don't know what is the shape and morphology of the protoplanetary disk. And now we have a wide diverse nature of protoplanetary disk revealed by the ALMA. And I'm actually working on the Event Horizon Telescope, and that actually provided the first images of black hole. That was also very compact. It's previously just point, and the first image is still blurry. It's like a donut, but it already tells us a lot about the space-time around black hole, and then how plasma around the black hole is actually falling into the black hole or sometimes escape from the black hole. So imaging is in general very powerful to reveal structures of your target cells without a specific source model, and that usually have a really rich information. So how we actually make images in the radio interferometry. So there was a very nice talk in the last time by the Lucy Lau, but let me just give a quick recap of that. So what we are doing in a radio astronomy is that we ultimately want to capture images on the sky like this, but the radio interferometry cannot capture image directly like digital camera or optical telescopes. What we are doing is that we are sampling information of images in the Fourier domain. And we usually call the Fourier component of image as a visibility. That's a radio astronomy jargon. And here I'm just showing the rotating arcs seen from this target source, M87, for the EHD. You can see actually many telescopes here. And you see the lines connecting between two telescopes. And this is so-called baseline. And what we are doing with the radio interferometry is that the radio interferometer samples Fourier component at the spatial frequency corresponding to the projected baseline seen from your target source. So if you have multiple telescopes at the different separation, you can sample the spatial frequency with a different frequency and also different orientation. And also another thing is you can actually realize that with Earth rotate, the projection of baseline will rotate and slightly changing the length because of the change in the projection due to the Earth rotation. So this also allows you to sample wide area of the spatial frequency only with the single baseline. So in the case of EHT, we have this kind of coverage. This is super sparse because we do not have a lot of telescope on the Earth, but it still capture many spatial frequency well enough to characterize basic morphology. For instance, there's a null region that actually defining the ring diameter, and you see an asymmetric image, and this is also seen in the Fourier domain. And this isotropic coverage is actually enough to capture this kind of basic morphology. So that's why EHT was able to make the first images of black hole. But on the other hand, in general, we expect is that because we do not, telescope everywhere in the Earth, or if this is even true for the connected interferometer in a smaller scale, like ALMA or VLA, still we have, some point which we do not sample in the Fourier domain. So the basic nature of the radio interferometric observation, it's a sparse coverage in a frequency domain. And if we actually formulate this in a mathematical way, this is just a simple linear equation in an ideal case. So we observe image, and the interferometer works as a partial Fourier sampler, and we have data. And in ideal case, we only have a statistically independent thermal noise, generally following the normal distribution. And but the equation is very simple, but the issue here is, as I said, the sampling is not perfect. So the number of the vector here for the data is actually less than number of images we want to solve. So therefore, this linear equation is underdetermined. As basically infinite number of images that can explain the data perfectly, even without this kind of uncertainties. So what we are doing with the interferometric imaging is that we try to pick up a reasonable, or I would say most conservative solution based on some prior assumption of what kind of images are more likely. This is actually fundamentally common for whatever the techniques like Queen or more new or forward modeling techniques. So one of the question is what is the prior assumption and how we pick up the reasonable solution. So the traditional imaging techniques is so-called Queen. That is in briefly speaking, that's a kind of greedy approach to derive a sparsity construction for given measurement set. This is actually very old techniques. The first one was actually given in 1974 by Hopcomb. And if you're not familiar with this Green, and if you're familiar with more computer vision techniques, this is a mathematically equivalent to the matching pursuit technique, which was developed in the 1990s for sparsity constructions. So the idea of Green, the prior of Green is that the most conservative or reasonable image should be explained by a very small number of elements. That the original technique actually used a point source, but now we have used a like a Gaussian with a different size, so basically an element from some dictionary within a given residual error. And Green is so-called inverse modeling approach. So let me explain why this is inverse modeling. So the idea of Green is very smart. So Green, the issue of the previous equation is that we have a small number of measurement set, and we do not sample some space in the Fourier space. What we do is that we just assume 0 for not sampled visibility and then inverse transform. So that is so-called the Darby map. This is mathematically corresponding to the ground truth image combined with the point spread function of array. This is a Fourier transform of the sampling function. And what you can see here is, so this in the Darby map, you can see some blind spot here. And that actually the shape looks resemble with the point spread function. So what we can do is that we can assume there is a point source here and subtract the contribution of point source, which is the point spread function. And after subtracting the point spread function, you start to see more fainter contribution from a different place. Then you can put point sources, subtracting, doing this kind of iteration, and you can see, more fainter contribution, and and construct a better model. So we do this kind of iterative procedure mainly on the image domain. So this is the reconstructed video image. In general, clean actually pure model map actually over resolving the structure, because it uses a point source or compact Gaussian or etc. And sometimes it's not realistic. So what radio astronomy people doing is, after reconstructing a model images that usually matching with the data, they slightly blur at the resolution of interferometer. So this is the kind of final image, and this is how clean works. So I just picked up another slide from the last talk by Basi. This is actually a very nice slide outlining how clean optimization is doing. So as I said, what clean is doing is basically taking the visibilities. This could be observational visibility or a residual, from some given model, and then graded in the Fourier domain. And so so here, we have some data, but where we do not have data, that is just 0. And then inverse Fourier transform, they're getting a residual dirty image that is convolution of model image with a point spread function, or residual image with a point spread function, and try to actually get the good model image in the image domain. This is so-called minor cycles. The great thing is it's utilizing the image of point spread function, so it can be done purely in image domain without Fourier transform. So this is so-called minor cycle. And sometimes to correct some errors coming from grading, or just an error in the subtraction of point spread function, it's going back to the Fourier space, and recompute residual visibility and doing this again. This is so-called major cycle, which is more computationally expensive. But anyway, the great strength of clean is it's very computationally fast. Minor cycle doesn't need FFT. Images can be solved in purely in an image domain. And it's shown to have a very good performance for well-calibrated data and with very good coverages. And there are actually many extensions. As I said, original technique uses a point source as just a dictionary, but it also uses now Gaussians with a multiple size. This is so-called multi-scale clean. And also, the OVC actually was, pioneering the multi-frequency clean that actually combine multiple band to get a better frequency coverage. And then also there are, some implementation of wide field of effect, so-called A projection or double projection, to correct some direction-dependent effect happening for wide field of view imaging. I believe actually this will be covered in the next talk in December by Maxim Voronkov. So stay tuned for the next month talk. So as I said, clean is a very smart technique, and it works very well for many cases, but sometimes actually clean is severely limited. So as you see, clean is utilizing the residual map. So that's coming from complex visibility or residual complex visibility. And another one is it's utilizing the point spread function to deconvolving, particularly in the minor cycles. So if actually both of them or either of them actually have a very bad performance, then actually the clean does not work. So this is a clear limitation of clean. So one case is the data is highly corrupted by residual calibration errors that is relevant for high frequency observations, where atmospheric calibration is challenging, or long baseline observation as well. And this is typically the case for very long baseline interferometry, which is often lacking the absolute phase information, lacking calibrators, and also beyond the radio interferometry, optical interferometry completely missed the absolute phase information. So this is the case for some challenging calibration cases. And also another thing is it's using the point spread function. So if UV coverage is too sparse to create a good synthesized beam, then it doesn't work. I mean, the convolution is actually very poor. So this was actually the case for my project, Event Horizon Telescope. So this is a kind of ARIA prediction. If we have black hole images compared with the resolution of the interferometer, then even with the ideal case, the convolution sometimes doesn't work very well. So this actually drives newer imaging techniques. Let me just also show how data can be corrupted for the residual calibration errors. Actually, there are many factors, but I will just simplify to the most representative one, which is so-called complex gains. So here is just I'm showing the ideal measurement, shown in the previous slide. This is a complex Fourier component of the image. And so the phase, this is a complex number, and the phase of this number is related to the time delay of the signal arrival between the two stations. But if you have some turbulent atmosphere like this, then different a pathway of the atmosphere induce additional delay, and then that actually is turbulent and time changing. So that actually corrupt the phase of the information. So that can be corrected very well for some arrays, but for some cases like high frequency observation, long baseline, it's very difficult to calibrate accurately. So phase sometimes very corrupted. And also magnitude of the Fourier component sometimes also corrupted. This is also related with the sensitivity measurement. So we basically measure the signal strength in the voltage, and in some way we need to recover, to the real radio emission strengths, and that actually using generally based on the sensitivity measurement. But for instance, the signal path actually along with the atmosphere is affected by atmospheric absorption, or sometimes for some reason in instrumental issues or for atmospheric issues, the pointing of the telescope is bad. So sometimes the telescope's sensitivity actually is not optimized for the target source direction, and that causes the loss in the sensitivity, for instance. So this kind of errors also induce some corruption of the magnitude as well. So for instance, for our project, Event Horizon Telescope, for instance, the gains are corrupted by 10%, or some stations more than 50%. It's completely corrupted. And then the phase, we lose the absolute phase at all, and we can actually correct some time scale fluctuations, but not perfectly. So both measurements are corrupted, so we cannot use complex visibility as a good precursor. So that's the issue of, for instance, our project. So there are actually some additional measurement to handle this. For instance, if you have 3 telescopes and measure visibilities in the same time, if you actually compute the phase for this baseline and this baseline and this baseline, so basically the closed triangle baselines, and summing up the phase, then you see contribution of calibration errors will all cancel out when you're summing up. So this is so-called closure phase. This is actually pretty robust. It's only affected by the sky structure, so the true source nature, and not free from the calibration gains. And then also we have a very similar quantities for the amplitude. If you take the ratio of this kind of closed full combination of baselines, then it's actually canceled out, and we can actually get the robust information of source structure. So this kind of data also can be used for the imaging, but of course, with clean, it's very difficult to utilize this kind of data quantities. So that's why we developed a new imaging techniques, which is slightly different, actually different from the clean, which adopting inverse modeling. As I said, clean basically inverse transform from data to image and try to solve the best image in the image domain. And sometimes clean actually need a user guidance for which area actually contains the true source emission. This is so-called clean box or something. And also another thing is that if the data are corrupted, so what actually clean is doing is once you reconstructed image from some corruption data with corruption, assuming that this image is actually closer to the ground truth image, actually solving gains or calibration errors based on that image, then actually calibrate data and reconstructing image with the clean and calibrate again. This kind of cycle is so-called self-calibration. So this is the way actually clean handles the corrupted measurement. But this may be actually challenging for the EHT because of the degree of corruption, and also it's very difficult to incorporate the uncertainty or gains when we reconstruct image because of the nature that images are also on the image domain. So that's why we develop newer imaging techniques for the EHT. This is taking a forward modeling approach. So what we're doing is that in each iteration, images are basically transform to the data based on the measurement equation. And then images are compared with data purely in the data domain that allows to incorporate, many observational effects, or even we switch the data product to the closure quantities, not the complex visibilities, and derive what likely the image is based on the data domain. And we can incorporate the prior assumption for images. For clean, it was a sparsity, but we can actually incorporate, different prior if needed. For instance, the non-negativity in the image. This is actually a very straightforward one for total energy emission. And the sparsity like clean, or we can actually constantly, enforce the piecewise smoothness on the images. Or there's another method, incorporate information entropy, so-called maximum entropy method. But overall, imaging method actually is described in this way. So basically, there is a likelihood term of the image based on the data and measurement equation, and there is another prior on the images. So this is a kind of Bayesian-inspired optimization. But I said inspired because sometimes this P doesn't reflect the actual probability distribution, but it's kind of Bayesian-inspired. So this actually term, as I said, so this one is actually basically based on what kind of image is the most likely or conservative. There are a wide variety of the prior assumption. And also another part is actually how we solve the images. So there is a gradient descent method to make a point estimate of the image, or there are sampling method that widely survey the posterior space. So there are actually two kind of optimization to solve the images. So one of the method is a kind of gradient descent based method, so-called regularized maximum likelihood method that used in the EHT imaging. So this likelihood term actually is converted to the chi-square term for the RML method, and we can utilize actually various data term to fit the data based on your properties of observations. And another term is a regularizer that actually explaining, what kind of images are more likely. There are multiple options. The most classic one is the maximum entropy method using the Kullback-Leibler dimensions of image. And also there are more like a compressed sensing based regularizer like a total variation, and also the L1 norm that actually lead a sparse solution. And this is actually leading a sparse solution in the gradient domain. There are also some more like a physically motivated term, usually like take a squared Euclidean node between the target parameters and actual quantities. That could be a central location for VLBI, total flux density, or second moment, basically constraining the size of the emission. I just want to show just gallery of how each regularizer works. L1 norm basically works as a point source based clean. It's very similar to what we get with the clean. And also total variation and total squared variation, basically we construct the edge preserved smooth or edge smooth images. This one actually works pretty well for stellar imaging, and this one actually works for the gaseous object. Maximum entropy method is another classical technique. Now it's expanded to the polarimetric imaging by EHT Forks. It was actually used in actual science imaging with the EHT. There is another method based on machine learning using machine learned multi-scale multiplier distribution, but I don't go details today just because of lack of time. If you have any questions, just let me know. I can explain more details about that. And also prior to the EHT imaging techniques development, there were many compressed sensing methods are developed for a lower frequency array like SKA or pre-SKA array, and many methods using the compressed sensing, basically using the compilation of images with wavelet. So this is just a quick example. Here's a black hole jet images. It's very extended and multi-scale structure and very complicated feature. But if you take the wavelet transform, these complicated images information will be very compressed into a very small element of the coefficient. So we can actually enforce sparsity in a wavelet domain, and that actually finds to be a very good for various type of radio images. So there was a pioneering work 10 years ago about by the Vayax et al. But there are many methods actually developed for lower frequency array for using the multi-scale compressed sensing image reconstructions. So I just want to show some gallery of the actual application of techniques of the real data. I think one of the most active area of the forward modeling approach or forward modeling imaging is the Event Horizon Telescope and the millimeter wave VI. So this is the first images of black hole. Here I'm showing the clean reconstruction. It's just blurry because of the the nature that it needs restoring with some Gaussian. But these are actually newer imaging techniques that are actually showing the sharper images. So the famous black hole images is actually blurring, just taking a conservative approach, just matching the resolution to the previous the traditional method, and actually averaging of a different method to just to show the representative morphology seen in all the method. But generally, the newer techniques are actually showing the sharper images. One of the power of the forward modeling images is the closure-only imaging, so calibration-free imaging. So this was actually a very important part of the first imaging of a black hole. So here, this is showing the reconstruction with the new technique. So this one actually using absolute amplitude, but it doesn't use absolute phase information, only use a closure product and amplitude. But here is even actually without absolute amplitude. So it's just using the closure quantities, not using any calibration information. Then it's still actually able to recover this link-like morphology. That was actually a very important narrative part of our imaging paper. And also the RML or newer imaging techniques is now applied to the other independent imaging array. I'm showing one of the first example for the protoplanetary disk imaging from Yamaguchi et al. There's another paper for another object recently, but I'm showing the first the results here. So here is the protoplanetary disk image from ALMA. This is for HD 142725. So this is a kind of blurry beam, and if we just make a slightly smaller blurring beam, then this actually basically gives a super resolution, but you start to see an artifact from the method. So for multi-scale clean, you start to see a compact artifact from the point source or compact Gaussians used in a reconstruction. And this is the reconstruction with the regularized maximum likelihood. And what we can see is even with a sharper beam, it's actually provide a piecewise smooth images. And the exciting thing is this is from the very compact array, and ALMA can change the spatial frequency coverage. So if we have a large frequency coverage with a finite beam, then you can see how this is correct, how correct this is. Then here's the image with the another observation at the same frequency with the intermediate configuration. Then now you can see that actually the forward modeling approach with the compact configuration provide a very reasonable image compared to the actual image from the higher angular resolution observations. So this basically kind of a proof of concept that forward imaging may allow the modest super resolution if the source structure and signal to noise ratio of data allows. And there's another application for ALMA imaging. So this is a very famous HL tau protoplanetary disk images. This is actually reconstructed with clean and self-calibration, as I explained. And this is the closure-only reconstruction. And this is actually not blurred at the restoring beam. So this is the model image. And this already recovering the basic feature seen in HL tau. And what we can do is, because closure product it have a low SNL, we can do is self-calibrate data with this image and the image with the full complex visibility. So this is the closure only the self-cal image. Again, this is not blur the beam, but it still actually recover piecewise smooth disk image. And then one of the striking thing is here in the original green images, there's some gap, and also there's some missing thing in the outer disk area. But basically the forward modeling approaches provide more symmetric images. I don't say that this is the more real images, but this is actually capable, maybe actually capable of a more robust reconstruction, not affected by the convolution beam, even for the this kind of dense array like ALMA. There was some application for simulation of NG-VLA. This is the simulated observation of the Betelgeuse with the next generation VLA, which is still in the concept stage. NG-VLA is a huge array. It has more than 200 telescopes. And it generally have a very good coverage of array, but still sometimes RML is actually better. So this is the reconstruction with Kreen. This is already provided very fantastic images, but the RML or forward modeling approaches even actually provide sharper images in the many reconstructions. So so even for the future array with a massive number of telescopes, still maybe the forward modeling approach actually provide a complementing science cases with high fidelity imaging. So another frontier of the forward modeling approach is the multidimensional imaging. This is definitely needed for the Event Horizon Telescope because one of our primary target, Sagittarius A star in our galactic center, actually is a bit kind of a toddler. It's actually changing a structure within 20 minutes or even shorter. So basically each frame of image is corresponding to the 10 second or something, and we do not have a very good coverages. So we actually have been developing a 3D imaging techniques that reconstruct the movie from simultaneously for single data set. This actually shown to be actually provide a better reconstruction for.
Kasu, you have 5 minutes left.
Okay, yeah. So we have a Okay, yeah, we'll speed up and finish. So this also have a great potential to improve multi-epoch observations. So this is actual reconstruction of the radio jet of M87 with taken by the very long baseline array. Here is the reconstruction of Kreen, and this is done by like individual reconstruction. So each frame images are reconstructed from each epoch. And if we combine all the data set and reconstruct with the 3D imaging techniques, here is the reconstruction. So this is using the same data set, but you can actually see that many artifacts coming from each observation is suppressed by combining the many data sets simultaneously. And also you can see some advantage of forward modeling techniques, basically providing sharper images and more realistic images. So you can actually see better reconstructions. So these techniques are inducing additional regularization. So for instance, if you have a very good coverage, time coverage of data, we can assume that each frame is similar. So we can regularize distance between adjacent frames by Euclidean norm of each image or relative entropy. There's another smarter technique solving a cross-form approximation at posterior. So this actually derived the exact inference of the posterior using multivariate Gaussian process. But anyway, so one of the class of techniques is using the transitional probability or frame-to-frame image distance. If your time coverage is not enough to regularize the distance between adjacent frame, another way is regularizing the image distance to the mean. So reconstructing the mean image and also regularizing the distance to the different frame. This is also a measurement method used in an Event Horizon Telescope now. And also another frontier, apart from the multi-dimension, is a Bayesian imaging. So regularize maximum likelihood just give a point estimate, but we also want to assess the uncertainties for direct utilization of images for science. And the most classical technique to do it is the Markov-Chain Monte Carlo. There are actually many methods developed for the EHT, but I would mention that this is not the first one. There was already a techniques developed for using the MCMC for low frequency astronomy, mainly developed in the 2010s. So in the last decade, but the actual science utilization is also happening in the EHT world. And MCMC is computationally expensive. So current actually frontier is actually variation inference. It's more computationally less expensive method. And there is a very exciting method actually using a variation inference using a neural network. This actually provides a better, faster sampling of the posteriors. They're one of the first pioneering work done this year by Sun and Bauman. This actually techniques also allows the simultaneous modeling of imaging and calibration effects. So it can assess how calibration effect assess the result on images as well. So this is a nearly final slide. So I just want to summarize pros and cons of forward imaging method. As I said, the inverse modeling approach is great. But actually there are some pros on the forward modeling imaging method. So it uses measurement equation and solve images directly in a data domain. So generally it is actually have a good advantage to maximally extract the source structure seen in the data. That sometimes leads to modest super resolution. We have a flexible choice of data and prior assumptions. that allows flexible imaging and also mathematically incorporate various effects in imaging. And the Bayesian imaging method developed recently allows also more rigorous estimate and a direct inference of the posterior distribution, which is actually exciting for the now. I think the primary concept of these method is a computationally expensive. This was not in the 1970s because it's very just computationally expensive, and we do not have minor cycles where we can solve images in a purely in the image domain. And also most of current foreign imaging packages are not yet scalable for general imaging for ALMA or larger arrays, NGBLA, BLA, SK precursors. So in my view as a radio astronomer is that both methods are pretty useful for the future array, but in a different area. For instance, like if we want to image huge number of pixel images over the wide field of view, I think for the imaging is just too much computationally expensive. And in general, this kind of science can be enabled by the excellent calibration and UV coverages. So this is actually where QuEEN works pretty nice, and this could be so that's why I believe that QuEEN is still the main method for the NGBLA main array or square kilometer array. But if we go to the higher frequency or longer baseline, if we want to make accurate imaging of a compact source or better modeling of imaging structure, simultaneous calibration imaging, this is actually where for the imaging actually have a powerful advantages. This is the main field of next generation event horizon telescope, or even actually intermediate or long baseline arrays of the next generation interferometers. And I believe there will be a very nice talk in December by the Maxim Voronkov for wide field of view imaging, particularly for the QuEEN method. So I also just want to summarize the kind of major challenges in the forward imaging. One of the things is the cost of dimensionality. So radio astronomy images, as actually Ubusi Lao's talk, very well outlined, we have 5 dimensions, X and Y for 2-dimensional images, but we also have a frequency axis, polarization axis, and now we are doing also temporal imaging, so dynamical imaging, which involve time. So in principle, it could be 5 dimensions. And if we have a prior assumption for each dimension, one of the issues is how to determine hyperparameters or optimal regularizers, or ultimately how can we reduce hyperparameters to handle multi-frequency, multi-dimensional images. So I believe some ideas to be shared by the next talk today, from the MRI imaging, which is already handle multi-dimensional imaging. So thanks for listening, and I will take just brief questions.
It seems to me one of the obvious cases of overlap are EHD observations of time variable Sagittarius star. They want you to comment on that.
Yes. So for the application of the time domain imaging, EHD actually is definitely wants to actually make 3D reconstructions for Sagittarius A star, one of our primary target. But I would say the application of these kind of time domain techniques is also not limited to the EHD observations. For instance, the community of the stellar imaging with a very large array or ALMA actually wants to also reconstruct 5-dimensional imaging with a very short time scale. So what they are doing is basically they are currently doing snapshot imaging. So basically just pick one frequency and one chunk of time and reconstruct image with QuEEN and try to make a video in a frequency domain and also image domain. That is also happening in more like also the compact objects like so-called microquasars that also have a very short time scale of hours and that's still this is actually where probably the next generation instrument will explore as well, and with a better sensitivity and higher angular resolution. So I think the need for better handling of this kind of multidimensional imaging will be actually enhanced by the next generation instrument, not only limited to the EHD.
So there's a quick follow-up. It says, do you have a sample data set that someone could use as a challenge and try different techniques on it?
Yes. So EHD collaboration, or there is also another collaboration to develop the idea for the next generation event horizon telescope. And both EHD and NGHD hold the imaging challenge. So basically, it's actually kind of blind imaging challenge where organizers provide the data only and without telling what is your ground truth model, and doing things in a blind way. So EHT challenges are kind of ended because we are now more moving to production stage, but NG EHT project is holding imaging challenges, and everyone can just attend. Yeah, I can point out. Maybe I can just I need to find a link, but I can point out where is the challenge website.
Yeah, if you can post it on Slack, it would be great.
Yeah.
Thank you.
Yeah.
Just can you elaborate on how imaging with closure phase only works? Is it something accessible to general users, and is there any good analog for medical imaging?
Yeah, I think that's a great question. So in terms of accessibility, there is a open source software developed under the Event Horizon Telescope collaboration. One actually, probably the most popular the software package is EHT imaging library. And also I myself actually developed a Smiley, which is another the forward modeling approach packages using the closure phases and also closure quantities. I can post a link there, maybe Slack channel, because Zoom chat probably is not the permanent place.
The Slack channel will last a while.
Yeah, so I can post them. It's in principle actually available for general radio astronomy users. Actually, some of the construction we showed today with the closure imaging is actually coming from these software packages. Is there good analog for medical imaging? So that's a good question. Actually, I don't know the answer. So I think some effect inside the integral of the measurement equation is actually very common. I mean, as Urbasi explained, and also that was explained by Vlad Talks. I actually don't know if MRI generally have this kind of direction independent effect, which is kind of like a station gains or something. This actually makes it a little bit difficult to apply, the convex optimization algorithm, only works for, complex visibility and the Gaussian noises. I actually do not have a good idea if there is a similar problem actually happening in the medical imaging. Maybe Vlad, you can answer that.
Yeah, I was just thinking too. I don't know. This is something that happens before you get to K-space, so it seems like there's there's less similarities there, and there are other people probably on here that actually have experience on both sides that may be able to actually answer the question. But it would be interesting to look at. We do have antennas. We do worry about phasing things to get things to go back together in order to form our information. We usually keep those separate in K-space, but I'm not sure if there's an analogy or not.
So I think the question of what I didn't answer is elaborate on how imaging with the closure phase only works. I just want to make sure that the closure phase only imaging probably shouldn't work. We need some information about magnitude of the Fourier component, amplitude. That could be just absolute amplitude, with some additional budget if there is a systematic errors, or closure amplitude if we don't want actually relying on the amplitude at all. So my general expectation for closure only imaging is, of course, first of all, this only works for high signal to noise ratio data. If your measurement is actually doesn't have a good SNL to form closure quantities, of course it doesn't work. So this is still only available for some limited amount of sources, with the good SNL, enough to utilize the closure quantities. That's probably the first point. And then the second point is that the closure imaging basically involves a closure quantity. That actually, generally the ratio or sum of the 3 or 4 independent interferometric quantities. So basically have a low SNL. So my experience with the EHT or synthetic data, or some imaging with the longer wavelengths via VI, is that it generally not suitable for super high dynamic imaging, high dynamic range imaging.
Okay. Okay. Thanks, Kazuo. I think for the rest, I'll ask the person who posted the question to take this up on Slack with you, so that you can give them a more detailed answer offline if that's possible. Thanks a lot, everyone. This was great.